Very good morning, my dear students. So again, here we are going to solve the different types of problem. That is a problems on a spring mass damper system. Okay. So I already told what you mean by spring and what is the importance of spring and mass damper. Okay. These are the basic element or these are the what the basic component of a spring that is a vibration system. Okay. Well, sometimes they may ask you what is the basic component or basic parts of an element, what the mechanical system. Okay. So you have to write this spring mass damper. Okay. So here today in this class I am going to solve the numerical problems on spring mass damper system. Okay, so first problem given like this. Okay, so before solving any problems under this module 4 and module 5, that is a part second, that is a vibration part. So you have to remember the list of formulas first. Okay, so what you mean by C, what you mean by K, what you mean by zeta, what you mean by N, omega N, D, zeta, over damp, under damp, critical damp, like this. You have to remember the notations and formulas, then only you can go for solving the problems. Okay, so here today class, this is also very important. So this question I have taken from the university examination only. Okay, so problem 1 I will read like this. Okay, so determine, so I have to find the critical damping coefficient, damping factor, natural frequency of a damped vibration, so logarithmic decrement, and the ratio of two consecutive amplitude of a vibrating system which consists of a mass having what 25 kg, spring stiffness 15 kilonewton per meter, and a damper C. Okay, the damping provided is only the 15% of the critical value, so that is what C is equal to 15% of Cc, they given like this. Okay, so one mechanical system is there, so that is fixed within a mass of 25 kg and 15 damper. Okay, which is provided to C is equal to 15% of Cc. Okay, so you need to calculate all these factor. Okay, so I told you what you mean by critical damp. What is the symbol for critical damp coefficient? It is denoted by Cc. So damping factor is denoted by zeta. So natural frequency is equal to omega n. Okay, so logarithm decrement is equal to delta. Ratio of two consecutive amplitude means x1 by x2 you need to calculate with the help of these quantities. Okay, so first step is note down the given data. So given data is equal to mass is given 25 kg. Okay, so spring stiffness is denoted by K, small k, 15 into 10 to the power of 3 Newton meter. So here given, so Newton 15 kilo Newton per meter. So I have to convert into this kilo into Newton per meter because SI unit only. Okay, so now damper provided, that is C is equal to 15% of the critical value. That means what, here the C is equal to Cc 15%, they given like this. Okay, with the help of this quantity, with the help of these values, we are going to find all these values. Okay, so before solving all these three factors, we need have some basic formulas, some basic value we need to find. Okay, so here the given damping provided, that is 15% of the critical value damping. Okay, so here also I am going to use the only the TV Goda book. Okay, so vibration, that is the first edition 2013 August. Okay, so here they given the damping provided is which is equal to 15% of the critical damping. So damping is denoted by what? C. 15% is of critical damping, Cc. So C is equal to what? 0.15 Cc. Okay, you need to find first this one. Okay, so next, omega n is equal to square root of k by m. So we have the formula with us this. Okay, so substitute here k is equal to 15.10 to the power of 3, they given here. Okay, 15 into 10 to the power of 3 Newton, and mass is also given 25. So substitute here omega n is equal to square root of k by n. So spring 15 into 10 to the power of 3 and divided by mass is equal to 25. So you are going to get omega n is equal to what? 24.49 radian per second. Okay, so we have now we calculated what? C and omega n. Okay, so now we know that this is what so C is equal to 0.15. So C by Cc is equal to what? 0.15. So this they given, you have to use this wherever C by Cc is there, you have to substitute 0.15 from this. Okay, so that is C by Cc is equal to 0.15. So now go for calculating the each individual. Okay, so now we have the formula what? Critical damping coefficient is equal to what? Cc by 2m omega n. Okay, I already told this while deriving the equation, wherever Cc is there I am going to use this. Okay, so we have the mass value and omega n value, so we calculate, use this formula, we have to calculate the Cc value. Okay, so substitute here 2 into mass is equal to 25, omega n is equal to 24.49 radian per second. Substitute using calculator, we are going to get Cc, that is critical damping coefficient, is equal to what? Cc is equal to 1224.7 Newton second per meter. So this is what we are going to get the critical damping coefficient. So you have to remember this formula, or one more formula is there for Cc, that is 2 square root of mk. Okay, that also you can use the formula here. Okay, now second one is asking about damping factor. So what is the formula for damping factor? So damping factor is equal to zeta is equal to C by Cc, but we know this value C by Cc is equal to what? 0.15. So wherever C by Cc is there, just you write here, so you are going to get zeta is equal to 0.15. Otherwise we can use this formula also. Okay, 0 C is equal to what? 0.15 Cc by Cc, Cc going to cancel, so remaining you are going to get 0.15 only. So this is the zeta value. Okay, we calculated what critical damping coefficient and zeta value, we both we calculated here. Okay, so next one is to find the natural frequency of a damped vibration. Okay, so we have the damped natural frequency is equal to what, omega d is denoted by damped natural frequency, which is equal to omega n is equal to square root of 1 minus zeta square. Okay, so omega n also we have and zeta value also we know, so substitute here. So we are going to get that natural damped frequency is equal to omega d is equal to 24.22 radian per second. So this formula is very important well upcoming problem. Okay, so we have to remember this. Okay, undamped natural frequency or damped natural frequency is equal to omega d is equal to omega n square root of 1 minus zeta square. Okay, finally the next one is they are asking what logarithm decrement. So logarithm decrement we have with us the four formulas. So here they given we know the zeta value, so you can get easily the logarithm decrement. Okay, so it is denoted by delta. So delta is equal to 2 pi zeta square whole divided by square root of 1 minus zeta square. Okay, 2 pi zeta value we already calculated 0.15 whole divided by square root of 1 minus zeta square. Okay, so substitute all these values here, we are going to get delta is equal to 0.9533. okay, so this is what the logarithmic decrement. Okay, with the help of this formula. Okay, so finally last they asking what ratio of two consecutive amplitude. Okay, so that is a ratio of two consecutive amplitude is equal to what, if you draw one cycle here, okay, so maximum x1 x2, so they taken x1 by x2 is equal to what, so delta is equal to ln of x1 by x2. Suppose if they asking number of cycle means we are going to divide 1 by n. Okay, so remember that formula also. Okay, so delta is equal to ln of x1 by x2. Okay, so x1 by x2, so this logarithm goes this side means it will become power, that is e to the power of delta. So x1 by x2 is equal to delta value we calculated here with the help of this formula. So delta is equal to what, delta is equal to 0.9533. okay, substitute here you are going to get 2.594. okay, x1 by x2 is equal to 2.594. okay, so this is the ratio of two consecutive amplitude. Okay, so we calculated all the values. Okay, so see, that is a critical damping coefficient. Okay, damping factor, so natural frequency of the damped vibration, logarithmic decrement, and the ratio of two consecutive amplitude. Okay, this is very important problem, so we have to perfect the formulas first. Okay, so this is about the problems on spring mass damper system. Okay, so again this, I hope you understand this problem. Here nothing is there, just to remember the formulas, understand the question, note down the given data, what they are asking, where to find, on which formula you are going to apply. That is the main things in this vibration part. Okay, so now so that is about the first problem. So again I am taken one more problem here, that is a same problems on spring mass damper system. Okay, so sometime they may ask you what are the elements of a spring mass, that is a mechanical system. So you have to write these three, that is spring mass damper, spring mass damper. Okay, so here in the second problem I will read the question, second problem here. Okay, so for a system below, that is a mechanical system as shown in the below figure, this the characteristics of a dashpot. So dashpot is also same, damper is also same, both are denoted by C only, don't be confused. Okay, the characteristics of a dashpot is such that when a constant force of 49 Newton, so here a constant force, that is excitation force 49 is applied to the piston. So here piston, its velocity is found to at a constant of 0.15 meter per second. Okay, once mechanical system is there, if you apply some external force, that is 49 Newton, so its velocity is equal to what, 0.15 meter per second. So next, to find the damping coefficient, and would you expect the motion to be a periodic or aperiodic? Okay, so periodic means it will vibrate. Okay, so aperiodic nothing but it is a constant value, so there will not be a reduction of amplitude. Okay, so here so need to calculate. So here what they given, a constant harmonic force is given, that is external force is, that is Fd is equal to, that is the damped force vibration, the damped force is equal to 49 Newton is given, note on the given data, and the spring stiffness is also given 245 Newton per meter, and mass is also given, that is a 15 kg. So damping you need to calculate, and with a, when if you apply this force, the velocity is equal to what, that is x dot. Okay, 0.15 meter per second. So this is the system, this is the what, the mechanical system. Okay, so this is one end is fixed, this is the spring, this is the damper, this is the mass. Okay, spring is 245, damper you need to calculate, mass is equal to 15 kg. Okay, when if you apply external force, that is a constant for 49 Newton, velocity is equal to 0.15 meter per second they given. Okay, so with the help of those quantity, with the help of the given data, so you need to calculate here. Okay, so we know that the viscous damping force is given by what, normally the viscous damping is nothing but what, if the energy loss takes place in a viscous, that is a liquid medium, then you are going to call as, that is a viscous damping. Okay, that is a the direction of amplitude in a viscous medium is called as a viscous damping. Okay, so here the viscous damping force is given by what? Fd is equal to c into x dot. Okay, that is a damper into velocity. This is the formula is there, so you have to remember. Okay, damped force vibration, that is viscous damped vibration, is equal to c into x dot. Okay, we know that force, we know that. Okay, damped force is given, x dot is also given. We need to find the x, that is what? The c damper. So c is equal to fd divided by x dot. Okay, so fd is given 49, so x velocity is given 0.15. Okay, so c is equal to 326.67 newton second per meter. Okay, so now you calculate the what? The dashpot, that is the damping. Okay, we know that the damping critical damping coefficient is equal to what? 2 by square root of k by m. So k is equal to given 245 newton and mass is also they given 15. So you substitute here, so you are going to get critical damping coefficient is equal to what? 121.24 newton second per meter. This is the unit. Okay, so don't forget to write the unit in examination. Okay, so we know that the damping is, we know the, and cc is also know. So if zeta is equal to c by cc means we can calculate the easily zeta. Okay, zeta is equal to what? C by cc. So substitute c is equal to 326.67 here, what we calculated here, and cc is equal to 121.24. okay, substitute here, you are going to get the zeta value, that is the damping, is equal to what? 2.694. okay, so like this you have to solve the problem. Okay, the value of the damping ratio is greater than 1, the system is a overdamped system. Okay, and the motion is a aperiodic in nature. Okay, so if the zeta value is greater than 1, then such systems are called as a overdamped system. Aperiodic nothing but here there is a no change of reduction of amplitude. Okay, so that is what if you solve the, we are going to solve the upcoming, that is a graph. What do you mean by periodic? Periodic. Okay, so here like this you have to solve the problems on this, what? The problems on the spring mass damper system. Okay, so just here in this problem you have to remember this formula, fd is equal to c into x dot formula. Okay, so remaining all this formula you have to remember, already we know this. Okay, so like this you have to solve the numerical problems on spring mass damper system. Okay, so I hope you understand like this the spring mass damper system problems. Okay, so thank you very much.